Happened fast. I think we're live.
Oh,
Wow,
Ellie.
it's even showing up already. They're making changes at YouTube. I'm saying, yeah, look at that. We're streaming already. Hello, YouTube. We're
Hello.
used to
Hey,
a
Bill.
minute delay between clicking the button and seeing you all. And hey, Ben.
Yeah, I only just got it then, so I still have a minute delay, but I'm further away than you and on a I'm sure that whatever you stream to from your end, because you're in Jersey, YouTube's
Right?
probably smart enough that you're streaming to a regional
A
data center
local.
over there.
Absolutely. Yeah.
Yeah, so
Everybody
you're
does
getting
that.
it with so folks if you're on the East Coast, you're seeing this more live than I'm seeing it, but that's okay. So
So,
cool, we're alive.
yeah, how we doing? So, hey, I dug out an old PC board that, like many things, has a story behind it. So I figured we would start with that. This board here is literally how I became head of the TED project at Commodore because I had worked with this board at home. And what this board it was all Motorola, which I'm not a Motorola person. I'm a 6502 person. This had a Motorola like 6801 processor or something. I rewired it for the 6502, but it uses not a 6845, which it was like one of the common video graphics for composite. Love the 6845 monochrome though. The 6847, which was in some of the Tandy stuff, maybe even the Trash 80, Trash 1000.
Ah,
Oh, it was the color one, the 1000, something
yeah.
like that. Um, but it's a true NTSC output for video display. So it means it's got its own color crystal and all of the things you need to encode video onto a carrier. So, but the reason why I say that it got me my break at Commodore, let me see if I can do this, is prior to the way the 6845, the way you did access to the memory was you waited for the black edges, the vertical retrace time or the horizontal retrace. So horizontal's on the edge and then vertical's in the bottom. What that means is every time there's an NTSC frame, there's times during the frame where you don't see any video, and you can read and write to the RAM during that time. If you're not sharing the time on the bus, you're just sharing the bus. So that meant that the only time we could read and write to memory was during these retrace times. So I don't have something that shows the full frame, but it's real minimal. I mean, it's like out of 63 microseconds, you might get 6 or 7 microseconds, maybe 9, where you could write to the memory. And
There's not a lot of. I mean, it's eons of time by today's standards, but back then it was like this is a
it was 6
very.
cycles. Yeah,
It's
one
not
cycle
much,
per microsecond. Yes.
and this was a fundamental limiting factor of 8-bit animation. This is what
Right?
coders had to get around, and this is why the game developers in the 80s were the best programmers that ever existed. They had to bump every cycle they could
Every single cycle.
in
Yes.
every corner of the software because they had
Right.
these kinds of limitations. You could conceivably have a dual port memory, and this is what came a bit later on with 16-bit computers. They made graphics DACs. And
Right.
right, you'd have a D to A converter that would spit out the composite video, or a bit later on, RGB separate for a VGA interface, which
Right.
is
Right.
analog output, and it was a DAC, but the DAC would read out a line buffer. A buffer is another word for memory, from your video memory, and the thing that made video memory special was it was dual port, so the DAC could read from it, but
Right.
the host bus or CPU could write to it in parallel, and the DAC would read from it and spit out the serial analog for the video. And that was when we had moved to EGA and VGA controllers in the PC world and had more colors to choose from and things like that.
Right.
Um,
Right.
but that video memory, having just one memory, because memory's expensive, right? Animators realized you still couldn't write to it while the DAC was reading out a line.
Right, right.
Because otherwise you're changing things while it's reading it, and you get this peeling effect on your display where you see some things are moving, but you see some of the lines in those sprites are flickering as it goes across.
Right, right. I remember when the dual port DRAM came out, and we thought, oh my God, this is a godsend. This is what we've been looking for all this time. And I never used it. It always had enough issues that we just ended up splitting the bus in time. And that's, hang on, let me see if I can pull a picture up here. Oh, by the way, this legacy method is how the VIC-20 works. So the VIC-20, it did it the old-fashioned way, but then what the Commodore 64 did was it said, okay, let's run everything twice as fast, and we'll give this period of time. So let me back up a little. Normally in a 6502 cycle, somewhere during phi low, the address becomes valid, and then at the end of the cycle, the data is valid right here.
And that falling edge
locked
is
it
when
in.
you take the sample, right? Yeah.
Right. Right.
Yeah.
Yeah, now you had to meet the setup, meaning it had to be there like 45, 50 nanoseconds ahead of time. And then it had hold time. You see, I actually tried to show it.
Yeah.
There's like 10 nanoseconds you had to hold it after it. Because that was the technology of the day. Stuff wasn't instantaneous. You had to propagate. So what we did, though, is we said, okay, let's shorten things. And during phi high, we'll go ahead and wait till phi high, and we'll spit this process, the address out. It's just now it's late, but we have enough time to still latch the data at the end of the cycle. And that left us with this other half cycle of available that we did the VIC address. So we interleaved. So we went VIC processor.
I love
on
it.
almost every single cycle. Oh, it was wonderful.
So
This was what made the Commodore 64 be the best home computer ever made.
So in the hardware, how did you actually achieve this with the two devices, the 6502 and the VIC? How did you force the 6502 to not put its address on the bus until after phi high?
That's a great question. We made our own version of the 6502, and it had a bus available pin that could tri-state the outputs of the processor on the fly.
And that's the difference. One of the differences between a 6502 and a 6510.
It's one of the primary differences. The other being there is a zero-page port, a hardware port built into it. So that's really the main two differences of the 6510.
So what would happen if I had a C64 motherboard and I was looking for devices and I couldn't find a 6510 to put in it?
You can take a 6502 in a CPLD or an FPGA, or just a PGA and emulate it.
So I'd have to have that bus available signal, or
yes.
The whole thing
won't work. You have to have that zero-page port, or the whole thing won't work, because that's how it controls some of the things about the C64.
Right on.
Yeah. So here's this technique. Well, it turns out I had done this at home using this board you see here in the bottom left. I had wired it up. Matter of fact, so this started as a Motorola board. I converted it to a 6502, and then I wired the heck out of it to make it split bus. So, and this is actually using 2114 static RAMs. And this is a surprisingly small amount of wires, but it was a big amount of wires to do at home on your desk.
That's incredible. I love the PCB layout design of that. Look at the traces. So they use the classic 80s, even 70s double-sided PCB layout technique where you have horizontal bias on the top layer and vertical bias on the bottom.
That's right.
But I note one thing. Most of the traces are not at actual horizontal or vertical angles. So that to me looks like this board was manually taped out on film by hand.
Well, I'm sure it was. It was back before we had CAD. We were still hand taping back then, so I'm sure this is a hand tape.
Yeah. Now, today you might see boards like that are routed using, high-end routing tools or auto router like Topper, which does any angle. And you actually want it today, but for different reasons. Or maybe they are. I don't know. I could be wrong. That does look like it was done in CAD.
I'll tell you, we didn't. There really wasn't CAD available. There was SciCards and Applicon and Mentor were the three back then. We typically did hand tape these, but you can do a good hand tape job. You just put a piece of grid paper under your Mylar and use it for guides. A good hand taper will make it look like a machine did it in the array portion like this. So now what I love about it is this breadboard area is so typical of the 80s.
Yeah.
See if I can get my
the prototyping area.
And I used it. And you could see, so 74 LS154, we were talking about that before the show. If people have heard of the LS138, a real common 3 to 8 decoder, there was the LS139, which was a dual 2 to 4 decoder. Well, these are their bigger cousins, that 24-pin chip you see there. That's the 74 LS154. That's a 4 to 16-bit decoder. And so for some reason, I thought I needed more than 3 to 8. So obviously I decode the heck out of some. Yeah.
So these are used on the address bus to divide the top address bits to get different sections of memory for either I/O mapping or what have you.
And even memory selection, because the memory, these are two 114s. They're probably 1K by 4s. I forget. They're probably not bigger than that. So I would have needed to select banks of 1K. So, and this board I was slated to make it into DRAMs, and then I got my job at Commodore, and it's like all home projects just stopped. It's like they served their purpose prior to that.
Yeah.
So, but so this is.
So what's the bus on the bottom of that? Is that just? So I assume this Motorola board was some sort of development kit, but
right. But this was
card edge connector on the bottom. Did that follow?
It wasn't a standard. No, it wasn't a standard. It was just a way to get voltages on and off the board, and so I would have had an edge connector. Do I have one around here? I have an edge connector around here that fits a Kim 1, and so it's like what's on a Kim 1. You have +5 plus 12, for your DRAM, for your static RAMs. And then, some address and data bus stuff probably came out as well. So, cool. But at the top of this, it actually has a coax output. Hang on.
That's your video out.
That's video out. Yeah. So, 6847. And again, because I knew this, I just happened to mention, are you sharing the bus between the VIC chip and and they're like, yes, how do you know about that? I'm doing it at home and I'm an excited long-haired kid. And, and by the end of the week, they said, you're the guy who's leaving said, you're the next guy to work on the TED product line. So. Oh, there was our first little freeze. So Ben changed his modem, everybody. We're hoping to have less freezes here if that was the cause.
Yeah, but I did just get one.
It's a small one, yeah.
But that's, you know what? So my conspiracy theories abound that AT&T doesn't like me streaming.
Probably not. They don't like uploads.
Kind of almost to exactly the 15-minute mark and then do it. It's usually early in the show.
Yeah.
So this is how we got all the colors for the TED for a $49 computer.
Yep. And there was it was beautiful. It was frickin' beautiful because up until then we had 8 color, 16 if you changed the brightnesses, And so we had 121 colors, and the reason it's not 128 is 8 shades of black is still black.
Yeah.
So we had a whole matrix of colors. It's just you see this one column is black, black, black. Right next to it are the grays. So yeah.
Oh, cool.
And Ted was a wonderful, it was supposed to be a whole family to take on Sinclair.
What was the marketing? Yeah, so what was the marketing target there? What was the product marketing?
This guy.
It was because text display, doesn't that mean it did not do graphics and sprites?
It didn't do sprites, but it did 121 colors, so it was a business family. This was supposed, and we had our own hard drive that came with it, but we had our own monitor, we had our own printer, 2 printers if I remember right, and it was supposed to be a cheap business entry that wasn't supposed to compete with the Commodore 64. It was not meant to play games. It wasn't meant to do really nice sound. It had a built-in sound chip, but it wasn't meant to do sound like like a SID chip.
Right, but it was really for small business owners and VisiCalc and basically.
Yeah, and you hit it on the head. The word spreadsheet didn't exist yet. We used the words like VisiCalc and stuff to describe it. So
what are we looking at there? What is that device?
That is a TED chip. And we can actually see it up here in the corner. It says they put the word TED right on there for text display.
So now we know why TED Talks are called TED Talks. Is that it?
Yeah. So no, this was wonderful. This is like Commodore trying to make a single chip computer. This is the Raspberry Pi of its day for $49. Only it included the housing and the PC board and everything that goes with it.
You can't do that now. Like look at Raspberry Pi. You can get the hardware. You can get a really powerful computer on the bare PCB. But if you want keyboard and a nice plastic enclosure, and you're not going to 3D print it all yourself, there ain't no way you could do that even today for that money.
No. Let alone have pre-made software. There was programs for it. I'll give it that, because it was Commodore. We did have we had muscle in the industry, and we had a lot of developers for it.
Cool.
Yeah, Chris just said VisiCalc was far ahead of its time.
So, yeah, totally.
Yeah, if I keep telling the TED story. That's what it looks like. I took this through my own microscope. This is I think it's a TED. What chip was this? But this is what they actually saw when they looked through the microscope. And they would actually probe these parts with little whiskers. They had a stage where they could, a very smooth surface, and in the center of that was the chip in a jig that's powered it up and done everything. So we had to make it work on the end of a ribbon cable was the first challenge.
Yeah.
And then we had these little whiskers, and if the passivation layer was on there, they had to take the whisker and do we called it rape and pillage, to be honest. They would do this little back and forth and saw their way through the silicon nitride. Yeah. Mm-hmm. The passivation layer. Sometimes we had the chips made without silicon nitride on it. We could special order them that way. But then the chip would only be good for a week or two, is my memory. Not long. Mm. So it was a trade-off. So I think what we did was we probably ordered some without the silicon nitride, but as soon as those broke, we had to go back to rape and pillage mode.
And it's still pretty much the same process, just with much smaller whiskers and probes. And those
they emulate it now, and they build in JTAG. Yeah, they can simulate. We couldn't simulate. Well, we tried to do some simulation, but we didn't even have ERC rules. So we had design rules, right? Mm-hmm. If it got too close, we go, whoa, too close. You got to leave a micron in there or something. But if we accidentally made a good short, an excellent short, and this happened on the TED, where A10, A7, something like that, cut right across 9, 8, 9, and 10, it actually shorted all the address lines together.
Wait, how did that happen? Because these chips were also manually taped. They weren't designed with ECAD. They weren't designed with
Right.
Semiconductor CAD tools.
They missed it. You had to look at, so the way the designers would check a chip, here was the thing. You could be a brilliant designer, right? But if you couldn't sit down for 3 months with a scale, a little ruler, and sit there and measure each and every gate of interest and make sure they were the right length, and you know, a gate is, a transistor is just polygons overlapping exactly correct.
Yeah.
So they would measure the overlap and then look at the schematic and see if the length and width was what they had asked for. And this happened. They had a piece of tape cut right across the other ones when they were done.
Gosh.
In metal layer. This is in the metal layer, the layer 5. Layer 6.
Yeah.
I'm sorry, layer 6.
How often did this happen back then?
Every chip.
So
Every
it wasn't
chip at
like,
least one.
oh, you blew out this tape out and, well, they didn't call it tape out because they weren't using CAD, right?
They were using a CALMA. So, no, these were on a CAD called a CALMA station, but they were still hand-drawn polygons.
Okay.
So before then, they did cut Rubylith. We still had drawers of Rubylith, which is red film, and they would actually cut the overlaps and the diffusion zones and depletion zones and whatnot.
And even printed circuit boards were done with Rubylith by some
at one
people.
time.
Yeah.
Well, so I know that Sandy, one of the girls that worked the CALMA, came from PC board design. So it was a natural migration from PC board design into, it's just to add more dimensions. Nowadays, we're used to 6-layer boards. Back then, all PC boards were 2 layers, so a chip was like a 6-layer board. You know, you had to think in multiple dimensions. So, but the story behind this is, and you've heard this story, unfortunately I don't have any new ones. My second week at Commodore, they were troubleshooting in spite of this problem because it did cost $250,000 to make a batch of chips. And they couldn't write to the register to test NTSC mode. It would wake up in PAL mode. So it was our first chip that was both a PAL and NTSC. And the way the timing worked is if you woke up in NTSC, but it was a PAL crystal, it'd crash. But if it was a PAL crystal, if it was an NTSC crystal, and you woke up in PAL mode, it'd still work. So we would wake up in PAL mode and then flip to NTSC. So the way they couldn't test NTSC mode because they couldn't write to the register because the address lines, the selects, these guys, were shorted together. So they turned on the microscope light. And that's how I learned what they were doing. I was in their lab, kind of just watching, and the guy goes, turn on the light. NTSC mode, and the guy's, yep. All right, turn off the light. I'm like, wait a minute. Did you guys just use the photons from the microscope light to flood the register to flip it into NTSC mode? And they were so nonchalant about it. They were like, yep. I'm like, oh, you know, I'm working in the right place. I mean, we're using photons to get our job done around here. And they did. They troubleshot as much of the chip as they could. It took them like 3 revs before it was a workable chip. Something like that, about 3 revs. And then we ended up with maybe 6 revs total, something like that.
Yeah,
so but we just didn't have the tools.
Is still horrendously difficult and expensive.
Yeah. We didn't have the tools.
As much as the tools, the CAD tools and engineering tools that we use keep getting better and solving problems, new problems keep existing because we keep getting smaller and
oh yeah,
it's just a normal thing, right? So
right. Though they can do amazing simulations these days. You know, I'm sure the 86 family these days, whatever they're called, the Pentiums of today, they're simulated in ways that I couldn't comprehend, I'm sure.
They have products like Cadence has this thing called Palladium, and Mentor has similar things, where it's basically a big rack unit with high-performance compute boards that are covered in FPGAs.
Right.
They're all
Right.
they're all linked together, and they'll take what's going to be designed in implemented in silicon and do it first in the FPGAs, and they even use those systems for software development so that the software team can start writing the applications and driver code and all this kind of stuff that goes with the new chip before the chip's even gone to fabrication.
Right. Right.
It's
So
pretty crazy.
somebody asked, let's see if I can get the name here. Durango95 asked, did I know anybody on the assembly line? What was it like working in the factory? What was the factory personnel paid? I don't know what they were paid. But during the Commodore 64 era, before we bought Westchester, which is now the QVC building in Westchester, we tended to assemble in Japan. And the problem with that is there's a tariff for having a completed computer sent to you. So when we got Westchester, we developed what was called the Super Line. And it ran the full length of this huge building. And this building was so big that there was actual weather. There was these big misty clouds at the ends of the building where the weather mixed with the edge of the outside weather. And the line was so big that they had to, we called it the bridge over the River Kwai. Halfway down the line, they had this big scaffolding so you could walk from one side to the other. So if you worked on the left side of the line, you'd have to go up over this bridge to get to your workstation. That's how big it was. So it was really cool. When I first got there then, though, they weren't allowed, engineers weren't allowed down in production. The Commodore 60, I can almost remember the guy's name who put out the memo. It said, no. And they would come get us, the security guards, if somebody from engineering went down there. Well, it turns out I started, I inhabited all the bars in the area, but I inhabited the bar that was the production people inhabited. And I started the conversation going about, hey guys, we can help. I know why they didn't want us there. They were doing stuff they didn't want us to know about. They were soldering capacitors on the board to make them pass the tests and stuff. And it's like, but if you tell us, we can make it so you don't have to do that.
Exactly.
And so by the time the TED hit, we were welcome in production. And I knew the QA area. I knew the QA bosses. They learned that they could ask us about code because they'd failed the test. And it failed the test because the code was written bad, not because the part was bad. So we helped them with that. So it became a cultural change to think about it, to allow engineers in the production area.
Yeah, well, actually, and that's something that's encouraged today. I mean,
right.
I could understand back then what people were kind of protecting their turf and influence and trying to make everything look good. So they didn't get
and
fired.
They lived and died by how many they shipped. They were afraid we would go, oh, that's illegal, stop doing it, and then they would ship less, right?
Yeah, right. Or stop everything. Stop the press.
Right. I'm an engineer that wants attention. They were afraid of that type of thing too.
Yeah, so I get it. Engineers in most companies I've visited or worked at, engineers are welcome on the production floor as long as they don't interfere, which they're not. They're encouraged to be there because you've got to learn what's going on here, and you will see things that you'll do a design revision so that someone can hold a screwdriver straight down instead of at an angle to get that thing in.
Right.
So
right, and we had the screwdrivers that were torque sensitive that put it in, to just the right torque and then would slip and everything. So, my background was I started as a production technician, and then I got hired at Pennsylvania Scale Company. I got hired in as an associate engineer because I knew some stuff about it. There's a whole different story. We'll have to tell it sometime. But then, so when I got to Commodore, I was actually I was from production. And that helped immensely in doing mass production of stuff. I knew how to select parts that wouldn't fail in the solder bath, things like that. So, and it's a lot of stuff you've talked about in the past about We were talking about ceramic caps versus tantalums and things like that.
Yeah.
So
That's
there's
cool.
my Commodore spiel for the day.
And so, I had fun with those decoders. You mentioned the one LS154
Yeah,
decoder
you had a
there.
story about the 154.
I remember when I was a new, still a teenager in college in the early 90s, and we were playing with
How
microcontrollers back
how
then.
how old are you, if you don't mind my asking? I forget.
I'm 46.
Okay, so you're 20 years younger than me. Not quite 20 years young. A generation. And I forget that. I forget I'm so freaking old sometimes.
You're
So,
very young, Bill. Come on. It's,
yeah, I'm in my 60s.
I recall uh, figuring out how to do, because I'd done motor controllers and power
Right?
supplies and things, switching power supplies. I was learning about all of that stuff at the time. So I'd learn about this thing, PWM, and I was even reading about Class D amplifiers, and being into audio and music, I was all about it. And then I realized, when I was in a digital electronics class one day and we did something with a magnitude comparator, or
Right?
we were looking at magnitude comparators, I'm like, oh, wait a second. This is a digital comparator,
Right? Right?
right? It's like a digital op amp, only it's not an op amp. It's not going to amplify, but it is a comparator that compares two binary numbers. That means I need to, bend over backwards. I don't need to bend over backwards to make a triangle or sawtooth wave generator, which is the normal way
Right?
you do it. I can actually make a sawtooth with a counter. And I'm like,
Okay.
well, okay, so I can do this thing. I'll share my screen and draw it, because it'll be fun that way. Let's see, what am I sharing? We're going to get the feedback loop of doom here for a sec. I'll bring up the drawing program.
Yeah.
Oh, look,
So
there's
somebody
loads of
asked
things.
Bard asked for a C128 story, and I'll have to say Bard will have to do the C128 on a different day, but because I'm getting ready for VCF East, I'll be definitely pulling out some C128 stuff maybe next week.
Yeah, so I'll just see if I can do this real quick.
Right.
So here's the deal, and I'll show you later where the 154 comes in. But you can have a magnitude comparator. You have a counter, another counter. I had let's just do. I'll put the 154 up here. Okay. I'll just do the pencil real quick. So these would be something like LS93s. This is like I forget the actual part number for a magnitude comparator. I want to say it's an 86, but I think that's just an XOR gate, which you can kind of do the same thing with an XOR gate.
Right. 86 is an exclusive OR gate. Right.
Yeah. So it's probably something like an 85 or something around there. I forget what it is, so I'll put a question mark. And here's the 154. And
So you the 85 you were saying is the magnitude comparator?
yeah, so you have A and B 4-bit inputs, and you have A greater than B, A equal B, A less than B outputs, 3 pins.
Yes, LS85. You nailed it.
All right, and so here I have just some sort of clock, like a 555 timer or something with a clock. And this counter here generates a ramp, so it just counts up and goes down, counts up and goes down. So if you were to graph the value of the binary output, so this is 4 bits, that's 4 bits, that's 4 bits. So it's only 4-bit resolution PWM here. So it gives you 16 levels from 0 to 15. Right. So whenever and this counter here I'd hook up, an up button to the up count. These are up-down counters. I put a down button. I'd have a reset circuit, and these could also preload a value of 4 bits as well. So I could have, a connector, or this could go off to some other system, and it could remotely preset the value. And so the output of this comparator, the B, would be whatever the set value is, and pushing the up button would make it go up, pushing down button would make it go down. And whenever this is A, whenever A is less than B, the A less than B output is 1 during this time, right? So that's your pulse width. And you could or that with equals if you wanted it to flip at the middle or before.
Right.
So that's a PWM output right there, and that was PWM, not PMW. I must be thinking about cars. So that's your PWM output there that would drive a MOSFET. Your inverse of that is A greater than B, so you could have a differential output if you wanted. And then what I would do was I'd feed that counter, the ramp, into the 154 and have all the 16 outputs here. You have a bunch of LEDs. You only need 1 dropping resistor because only 1 output is on at a time with a decoder. So you only need 1 dropping resistor for the LEDs, and all the LEDs are on the output pins. Right.
So it's only one at a time is going to come on.
You'd have your data input, and these are your enable outputs, 16 of them. And then you have this output enable, right? So if output enable is low, this works. If it's high, they all go to logic high, or 5 volts, and float. So none of the LEDs light up if that's high.
Right.
And so what I can do is say, only enable the output from the PWM. Actually, it would be the inverse, sorry. Let's delete that. It would be the inverse. So the LEDs would sequence one through the other while the output was high. And then as soon as it reached the set value and the output goes low, these turn off. And so you arrange your LEDs, in a circle of 16 of them. And because this is counting very quickly at, several kilohertz or whatever frequency, maybe 20 kilohertz, you don't see any flickering. It looks like they're all just lit up to the set point, and then they're off past the set point. And so this was my little model railroad control circuit. And
Okay.
then I realized model railroading is horrendously expensive. You need a lot of room. You basically have to be rich to do it. And it's not super conducive for a young man. I loved it as a hobby, but it was not going to help me get out there and meet girls. So I kind of gave it away.
Which is why I did lights for a rock group. It's and you were a musician, so there's
only so many things you can devote time to, and you just have to pick what's going to be the thing. And so I stayed with electronics, stayed with guitar, although I'm pretty out of practice just right now, unfortunately.
And I'm missing a finger, so my playing sucks.
So that's my 7.4 LS154 story. So
one of the things I did while you were talking is, because you said I put LEDs on a TTL output, you go, anytime. So I'm just sharing engineering thinking with everybody. Anytime that you have a non-logic part being run by a logic output, you got to realize that there's usually not a lot of current available. Sometimes there is, sometimes there isn't. Sometimes there's only 1.6 milliamps available. So I went to the LS1s. That's the LS85. I thought I was looking at the 154. But on the LS85, for example, we have 8 milliamps output, which is plenty to drive a TTL. I'm sorry, a
LED.
LED. Yes.
Yeah. LEDs, they usually have a maximum rated current of 20. Sometimes nowadays for the super bright
back then they weren't very
30.
efficient. Yeah.
But usually a standard rated current for an LED was 20, but you can drive them with less. So you choose the appropriate. I had like a 1K resistor. And sometimes those things in the data sheet are very pessimistic as well. Like the chip.
That's right.
The cans, sometimes you can actually push them way past, but this is recommended conditions rather than maximum. There's 2 sections in the data sheet you need to pay attention to.
And we see for the 154 that it's recommended 8 milliamps, so then we're still good. And there's usually an absolute section. I'm just not seeing. Oh, this is an excerpt. So normally there's an absolute operating condition also.
Yeah.
So very cool.
That was fun. That was a fun little design. And then actually that was also the first thing I did in an FPGA. It was like, because I knew that circuit, that way of doing PWM, so like back of my hand. So I first time I started learning VHDL and FPGA design, that was the thing I implemented. It was a comparator-based PWM.
Right. So I actually had something to show, but I've accidentally deleted the link here. So give me a second. And it dealt with music. Oh, it's a shame that I dropped it. So I was going to show a Leslie effect, and I don't have the link, but did you
had a picture earlier, right?
I had a picture, and now I got to find that picture again. Yes.
Oh, well, share your screen, and you can do that while we're watching you.
You'll see how bad you'll just see how bad I type. See, I've even mistyped Leslie.
Leslie. Or it'll be a Leslie speaker. Search for Leslie rotating speaker inside. Oh, there you go. You go to the history. there it is.
Go.
Oh, Pinterest. Okay, it's on Pinterest. This looks like someone made their own.
Yeah, it does, but it's still a Leslie, I figure. It's actually it shows 2 techniques for a Leslie. And then let's talk about what a Leslie does for us. But there, so at the top, we had the spinning horns. And at the bottom, we don't spin the bass speaker. We spin a baffle in front of it. Oh, stop. I'm not going to log into Pinterest, you morons. So I just remember seeing...
there are prefabricated audio power amplifiers or something.
Yeah. I just remember watching Emerson, Lake and Palmer, which is what what got me into electronics was my love of electronic music. And I just remember seeing all their speakers. Hang on. Let me, while I'm talking here.
Yeah, I love the sound of rotating speakers. So I'm a huge fan of progressive rock, and it's like the main keyboard sound in progressive rock.
Right.
Is a dirty Hammond with rotating speakers, so it's
with reverb on
it. It's distorted, kind of like Deep Purple-ish. And
I was thinking of Deep Purple when I was thinking of the reverb. Yeah, because
I actually saw.
What was the one where they?
So that keyboardist, Deep Purple, the organist who used these, his name's John Lord, and he wrote symphony
J-O-N.
concerto for a symphony orchestra. But the concerto instrument was not just a violin or the organ; it was the whole rock band, including the organ.
Right.
And I saw it performed at the Sydney Opera House with John Lord on the Hammond.
Wow!
Incredible,
wow.
Just amazing.
Wow! I still had the shirt, though it was a little tiny shirt. I can't believe I ever fit in it. I had my shirt from the 1974 Burn concert. So it had the melting wax heads of all the different.
I love it. So just
yeah.
going back to my age, that's the year I was born. At the very end, December 74.
And here I'm saying my dad actually took me, so I was probably 16 or something at the time. But yeah, I got to see Deep Purple when they were still Deep Purple with Ian Gillan. Yeah.
And, well, later on, they recruited one of my favorite guitarists, Steve Morse, famous for the Dixie Dregs and now Deep Purple as well. He is just one of the all-time guitar legends, Steve Morse.
Right. And I became a big Ritchie Blackmore fan after Deep Purple broke up or he left or whatnot. Yeah.
So what we're looking at here is something they didn't have DSP, and you would never think to do this with DSP had this physical effect not existed beforehand. So this is obviously someone making their own, and that's brilliant. I love it. So the rotating horn was using the Doppler effect.
That's right.
Right. So
to create a phase shift, a frequency shift, and a phase shift, and what I think of as flanging.
Yeah, or flanging and chorus, depending on the
chorusing, right?
Depending on the delay or how close you are to it. So what you get is one of the horn arms swings towards you. It's compressing the waves and going up in pitch and getting louder, a little bit louder as it comes towards you as well. Then it's facing you, and the pitch is at its peak, and the volume is at its peak, and then that horn starts spinning away from you again. And because it's physical, it's stereo, because the horn comes towards you on one side and away from you on the other. So there's a little bit of stereophony, even though it's a monophonic amplifier. So they were just brilliant. I don't know how they came up with this, Hammond or Leslie, but it was just such a brilliant invention because it added so much
depth.
tension. Yeah.
Yes. And so picture a wall of them too. So even now you're combining them, and they're in different portions of their spins, and the motor speed might be slightly different between different ones. And so it was a way to chorus, to thicken out that music by adding harmonically related content, but yet still at various phases to each other and whatnot.
And they tended to have two speeds, as I recall. They'd have a fast speed and a low speed, and you could set them with a dial, and that would drive the motors at two different voltages. So the organist, for an additional effect, you could flip a switch and they'd start speeding up, and then you'd flip the switch back and they'd slow down again. So I actually, although this was invented to go with organs and Hammond organs, it's become... I haven't heard it in a lot of recent pop rock.
Because you can do it in DSP, like you said.
But with some heavy metal and some progressive rock, it's still a very popular guitar effect as well. And so that's all done in DSP. So we have a chorus. So you take a buffer, it's a circular buffer, so you're putting audio samples into it, and effectively the simplest way to do it is you have a clock that drives your sample rate for the buffer, and you're continuously speeding up the clock and slowing it down, speeding it up and slowing it down, and that gives you the pitch change. But to get a true Leslie rotating speaker effect, you don't just need the pitch change. You also need two buffers for the stereo for each side of the horn, and you need to clock them and speed their clocks, or the speed change clocks. The low frequency oscillators have to be 180 degrees out of phase. Right. And so one's speeding up, and then those low frequency oscillators are also driving a voltage controlled amplifier on the output of each one. So as it effectively comes towards you, it's going up in pitch, but then it's also getting louder.
Changing
It
amplitude.
goes down in pitch and gets quieter. And all of that's done out of phase, and you take a stereo output of the guitar effect, and you get this stereo sound spread that's incredible. I love it.
You mentioned the 2 speeds, and I just remember there was kind of a whoosh, whoosh, whoosh noise you could get, and then there was a flutter noise at the high speed. It was like, whoop, 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 whoop. I just remember hearing those 2 different Leslie effects.
Cool.
And again, I just remember Emerson, Lake and Palmer with a stack of amplifiers, and when you looked at them just right, you could see the horns spinning at the top of each of the ones.
Yeah.
You had to look for them. You had to know what they were. So I Googled flanger, spelling it like I remembered how to spell flanger, and I remember why I spell flanger like phalanges with a PH, and that's because I used to build stuff from Paya. And
that's
we
right.
never knew how to spell.
Yeah, these are all like, open designs. You can build your own. They're kits. They actually, Paya also has, or Paya, I don't know how to say it.
However you say it.
Paya.
Yeah.
They also have a really popular theremin. And I've been wanting to build one of those for years. But again, it just goes to the massive list of projects I have that I don't have time for. But a theremin is a fun thing as well.
Right. And I had built one which had a linear controller on it, and basically it was an elastomer cut in logarithmic steps. And then you just took a probe and you'd go up and down it, and more or less equally spaced would be the notes. But it just sucked. It was okay for sound effects, but it was lousy for trying to play a song, But it had a VCO and a VCA, voltage controlled oscillator, voltage controlled amplifier, low frequency, all the little pieces of the synths at the time. But it was like anything. It also came with a lot of noise in it because it was only a circuit board this big, so it was single transistor circuits as opposed to 5 or 6 to make a real low noise VCO or something. So yeah, I forgot all about Paya till I Googled it just now. So what's your favorite pedals? Do you have favorite pedals for when you're guitaring?
I have there's a lot of pedals I really like. When I'm actually playing live, I do everything through an AXFX, which is kind of like what's that? It's like the flagship modeling device. So it has every pedal ever made. They've basically analyzed them. They use AI and all sorts of things to figure out exactly how that device responds to a guitar signal, and then they bottle it into an algorithm, and there's 4 DSP chips in this thing. It's incredible. So I use that because it sounds amazing. No one in the audience will ever know I'm using that versus actual pedals or amps. And it's just super high quality and very, very all I have to do is carry one piece of equipment that doesn't weigh much, apart from my guitars. But at home, I have some pedals which I've collected some over the years. I've bought some, sold some, and I always loved the Digitech Whammy. I actually recently sold one of those. I'd got it cheap because it had BS built in it. And the guy had replaced it with a newer device, and he was hocking it off for $200. And I totally cleaned up and restored it and sold it on Reverb for $450 or something. They're very very expensive because it's hard to get the original ones now.
I have an Elisa's cool. Microverb.
I remember those. I
have an old one of those.
I have.
So, and it's like you said, it's like just a pedal with a crap load of presets in it.
Yeah, or not even a pedal. So for these, this is a MIDI one, and you want a MIDI foot controller to go with it if you're playing with a guitar. Yeah, these were very popular in the late 80s, early 90s. Right. And then guitarists went away from rack gear for a while, and professionals keep using it though because it's better for road rigor. But most of the guitarists I know have big pedal boards with tons of pedals all over them, and they always have signal problems because between each pedal you have cables, and the cables is the weakest link in the whole chain. So I don't have that problem because I go through an Axe FX, but I enjoy fiddling with pedals at home and figuring out how to reproduce the sound of those classic pedals using the Axe FX.
Right.
So I have an actual my oldest brother who got me into guitar and electronics. He was an electronics technician for the Australian Broadcasting Commission. So ABC is a big government-owned television and radio corporation.
Okay, it's like the BBC for Australia.
It's like the BBC, but the Australian version. And he was an electronics technician doing tech support and repair work for anything and everything: radios, transmission equipment, audio amplifiers, mixing systems, you name it. Whatever they had in the studio and needed repair, he was one of the techs that did all the repair work. And he was an amazing guitarist, and he was 14 years older than me, but he was like my inspiration. And he taught me my first guitar lessons and taught me my first electronics. And he had some pretty outlandish pedals that are super rare. And he passed away in 1996 from pneumonia. But his wife gave me a couple of things that had been his that were just sitting in the garage, and they were broken. And one of them was a Gaiatone, which is a pedal brand from Japan from the 80s, TU2 overdrive. So it was a tube overdrive. So it had a valve and it had a 12AX7 in it as the heart of the whole thing.
Got it.
There were no other semiconductors or anything. It had true bypass switching. It had bass and treble, gain and volume, and the whole thing was built around a twin triode. And the tone and sound of it is absolutely beautiful. It's the best overdrive I've ever owned, and I will never sell it. And I hope that it becomes an heirloom in my family.
Right.
And what's even more special about it is it contains an AWA tube, a valve made by AWA in Australia under the Philips design license. So back in the 60s and earlier, Australia actually had its own tube manufacturing companies and factories in Sydney, and they made tubes for TVs and audio, and then for a while they also made semiconductors briefly. And there's the only fabs that I'm aware of in Australia now for semiconductors are experimental and boutique type, prototyping and one-off type semiconductor fabs. All of that went overseas. So it's kind of very special to me, and it sounds incredible. So that's probably my favorite pedal.
Right. I always thought of tubes as, you couldn't hurt them by overdriving either. I'm not saying you couldn't have too much cathode current or something, but, with transistor devices, you had to be aware of safe area operation, things like that. But with the tube, it was way more forgiving.
In a preamp sense, they are, but tubes in power amps do give out. They don't last. And that's why they, tubes.
Well, that's why I meant cathode current. Yeah.
They always
you get cherry red plates if you're not careful.
Right, and sometimes guitar amp manufacturers deliberately bias the tubes hot because they say that's the tone people want. It adds that even harmonic, or is it even or odd? Anyway, odd. I think it's odd harmonic distortion that's unique about a tube guitar amp. And so they'll deliberately bias the output tubes hot. But what it means is if you're playing regularly, like if you play once a week with that amp, you probably should be replacing your output tubes once a year. And that's pretty expensive because a set of matched output tubes is going to be $150. So, yeah.
Yeah. And we played outside one time, and the sun moved and hit our amps, and they all went click and shut off, and we had oh crap, yeah, we had to rig some awning on top of the amps to get the sun off of them.
Yeah, brutal.
So guess what time it is?
I can't believe an hour's gone by again.
Yeah. Well, it was fun. So a lot of good interaction on the chat group today.
Yep.
I've been chatting with different people. Chris asked if the Leslie had a pedal speed control. I never saw one.
I believe I've seen keyboardists use pedals for volume, but I'm not sure about speed. They may have. They may well have.
There'd be no reason they couldn't.
Yeah.
I just never saw one myself used that way. So excellent. Well, any final words, or have we? We beat the heck out of a couple topics here today.
Yeah. I guess I need to rest my voice a little. I've been talking a lot this week. I had a lot of meetings, and I just want to give a shout out to the Discord channel though before we go, because if anyone stumbles across this video now live or afterwards, after we're gone, and you're just watching this later on YouTube, make sure you get onto the Discord channel. There's a lot of
which
cool
I posted a link to it in the YouTube chat. The very first comment is a link to the Discord channel. We
should probably add that to the comments on the video too afterwards. I always forget to do that. We need a producer. Gosh.
Yeah.
If any of you are producers and want to help us out.
Or just if you're a social media interactor and you just want to help, just take the time to put, for example, we don't get a good description on our videos, so you can't search for it. Like this week, it'd be great if I had the time to go in and say, Bill and Ben talk about Leslie's and Motorola 6847. But the thing is, I'm exhausted by the time one of these is done, and I just go and I nemish, I just flop on the...
And I usually have to get back to doing stuff for Autodesk, but yeah, maybe I should just spend a little...
Yeah, it's earlier in your day. Yeah,
it's... Yeah. Well,
so excellent.
So join the Discord. There's always some cool stuff to discuss and interesting projects, and a lot of people are doing a lot of different things. Wes is just posting, was just posting from the 3rd. A week ago was showing about data books on diesel electric and electric locomotives and stuff like this, and maintenance guides and circuit diagrams from inside them. And I mean, there's just tons of interesting topics and discussion going on. So please join us on the Discord, and we talk everything about electronics and related technology, and even other stuff. We occasionally get into music, like we did just
science
now.
And music, and yes.
Yeah. So
excellent.
Maybe even pyrotechnics here and there.
I'll have to pull out my pyrotechnics pictures from Brownsville Station. I still have those around here somewhere. So excellent. Well, Ben, we'll see you here next week.